Okay guys, so the goal of this is to try and illustrate the importance of the center of mass when talking about the parallel axis theorem. So I'm going to quickly prove the parallel axis theorem for you and demonstrate why it's a very, very important piece of the puzzle. So you can't just use the parallel axis theorem and not take into account the moment of inertia about the center of mass. Okay. So here's what we'll do. So we'll say, all right, I have a system composed of, let's say 3 objects, 1, 2, 3. And I'll label them as such, 1, 2, and 3. Okay. And they'll be connected with these sort of rigid rods. Okay. So I can define like R12, for example, is equal to, first I need to make myself a coordinate system. So here's X and Y. And now I can assign locations or position vectors to each of my 3 masses. Okay, so I'll do that with a different color. So here, this is vector R1. It points to mass 1. This is vector R2. It points to mass 2. And here is vector R3. And it points to mass R3. Sorry, it points to mass 3. Okay? So I'm going to say R12, for example, is equal to the magnitude of R1 minus R2. Okay, R1 minus R2 is the vector that points from 2 to 1. So if I were to make a vector that looked like this, right, that's pointing from 3 to 1, this vector would be R12. Okay. All right. So this is the magnitude or the length. So this is really the distance between 1 and 2, and I say that this is constant. Okay, so this is what it means to be a rigid object, that the distances between objects that make the individual pieces that make up the whole object, the distances between each piece are fixed. Right? So I can write that in a slightly more general form and say that Rij equals constant, which is simply Ri minus Rj. Right? So I and j can be 1 or 2 or 3. Right? And obviously, then I have this. So it's just this, but with general indices I and j rather than 1 and 2. It stands for 1 and 2, 1 and 3, and 2 and 3. Okay? So this is what I mean to be a rigid object. Now further, I'm going to introduce one more vector. Right? I'm going to introduce, well, unfortunately, we have to introduce several more vectors, but I'm going to introduce the location of the center of mass. Now, recall the definition. If this is capital R is the location of the center of mass, then that means capital R is equal to the sum I equals 1 to 3 of mi vector Ri, and that must be then divided by sum I equals 1 to 3 mi. Right? So it's just a weighted average like we talked about before, which I can then write as this, just to be a little bit more concise. It's the sum I equals 1 to 3 mi Ri divided by capital M. And capital M is going to be the total mass of the object. Okay, so that's the location of the center of mass, and I will denote that with a black dotted line, and let's imagine that the center of mass happens to be right here. Right, so this is the center of mass, let's just say. Right? And I'll make a dotted line. This, that arrow points, and I'll call this vector r. Okay, so I've got all the vectors taken care of, except for one more. But as long as this is the setup, so if you understand this, then we're good to go and we can start grinding through the algebra. Okay, so these are all the definitions. Now, what happens if I want the moment of inertia? Right. So, first of all, I need an axis about which to calculate the moment of inertia. So let's imagine that I want the moment of inertia about, let's say, this axis here. So I'll dot. This is the rotation axis. Axis of rotation. Okay. Generally speaking, the moment of inertia about that point A, about this axis A, is equal to, let me see, the sum from I equals 1 to 3 of m sub I times, now I need the distance between the ith mass, so imagine the first mass, the distance between here and the axis of rotation, right? And that will be Ri vector minus, let's call this is the last vector I need to define, almost. Let's call this guy A. Okay, so this is the location of the axis. So this is Ri minus A. Ri minus A, for instance, R1 minus A is the vector that points from the axis to 1. So R2 minus A is the vector that points from here to here, and R3 minus A is the vector that points from here to here. And so all that means is that Ri minus A squared is the distance between the ith particle and the axis of rotation squared. So this is, if you recall, our definition of the moment of inertia. But we're going to do something kind of sneaky now. And I'll use my blue because this diagram is getting very cluttered. And I'm going to define this vector that points from the center of mass to the axis of rotation, and I'm going to call it little a. So man, we got a lot of clutter going on, but hopefully you're still following along. So I can write A, rather than calling it capital A, I'm going to call it capital R plus little a. Both vectors, obviously. So this is really equal to the sum I equals 1 to 3 mi times Ri minus, now I rewrite A as I said, so capital R minus little a. Because capital R plus A, capital R plus little a, is just that total vector, capital A. So capital R plus little a is the location of the axis of rotation. Okay, squared. Now I'm going to expand this, but the way I'm going to do it is I'm going to keep these guys together. And so what I get is the sum I equals 1 to 3 mi, and then the first term is Ri minus capital R squared. Okay. The second term is plus I equals 1 to 3 mi times little a squared. Okay. And then I have to add the cross term, so that's minus 2 the sum I equals 1 to 3 mi times Ri minus R dotted with little a. Okay? So let's take a look at this last term. Forget the 2 because it's not really that important. It's the sum from I equals 1 to 3 of mi ri minus mi times r. I've distributed mi in here. And all of that's dotted with a, but a is a constant, so I can take it out of the summation. But notice that r is a constant too, so what this really becomes is the sum of mi ri 1 to 3 minus capital M times r. All that's dotted with. Right? Because this second term is the sum of all the masses times r, but r is a constant, so it's just the sum of all the masses, which we define to be capital M, times that vector r. So we get this. But look, capital M times r is just this. And so we see that this cancels and happens to be equal to 0. And so what we're left with is that I is equal to the first two terms. Sum from I equals 1 to 3, mi ri minus r, capital R, squared. And then the second term, plus, look, the sum from I equals 1 to 3. A is constant, so again, we can take it out of this summation. This is just capital M plus capital M times a squared. Right? And then this term is 0. But notice that this is the moment of inertia about the center of mass, equals I center of mass plus m a squared, where a now is the distance between the center of mass and the axis of rotation, and there you have it. This is the parallel axis theorem. Let's take that a step further now. This is where it's going to get a little bit worse. So keep this diagram off to the side just so I remember. Hopefully you guys have written that down now. So what if I want the total kinetic energy? This is going to be tough now. So what I do is I say, all right, the total kinetic energy. So that's here is equal to 1/2 mi vi squared. This is the kinetic energy of the ith particle, right? So first, second, third particle, obviously, right? So really what this is I get the total kinetic energy. So I'll call this capital K is the total, is just the sum from I equals 1 to 3 in this case, but it doesn't really matter how many I'm adding together at the end of the day, of course. 1/2 mi vi squared. But let's take this a little bit further, and we'll write this instead. I'm going to stop writing I equals 1 to 3 because it's not relevant and it just takes up space. It is the sum of 1/2 mi. This vi is really ri dot, the time derivative of the vector ri squared. Right? And so another way to put it is equal to 1/2 times the sum of the sum of mi times d by dt of ri. And that then is squared. Okay. So what do? Let's again introduce the center of mass. Okay? And so I need to introduce more variables, more letters. So I'm going to stop referring to the position of the ith particle as Ri, and I'm going to instead write Ri is equal to capital R, which is the location of the center of mass, plus QI. Okay, and QI is going to be the vector that points from the center of mass to the particle. So let me redraw the diagram I did before, but without all those cluttered lines, because now I know exactly what I want to draw. Right, here's my coordinates, x and y. Here are my particles, 1, 2, 3. Right. They're connected with rods, but I'm going to make those rods dotted lines real quick because they're just going to get in the way. I know the distances between them can't change. Right. The center of mass is right here. Right. So this, I'll do it in blue. This vector is capital R. Right. This is the location of the center of mass. Let me label these 1, 2, and 3. And then, just to give you an example, this vector that points from the center of mass to particle 3 is called Q3. Okay? So I can write this guy being R3. Right? I can write R3 as capital R plus Q3. Okay? The reason this is going to be important is the magnitude of QI is going to be the same. Always, right? It is independent of time. It is constant because, again, the object is rigid. So the distance between the particles is all the same, or the distance between the center of mass and each individual particle is always going to be the same. Right? So, I have this, and so what that means is I can write d by dt of Ri is really equal to d by dt of capital R plus d by dt of Qi. Right? Now notice that Qi is not constant. I said the length, the distance is constant, right? So the magnitude of Qi is going to be the same, but it may be changing in direction, right? So this is not 0 yet, so you have to be very careful. Okay. So, what happens when we take this squared? Well, this squared, this squared, right? And so this is equal to, I'm going to switch to the dot notation to make this a little bit less messy. I'm going to have vector r dot squared plus the vector q dot, vector q dot squared, right, plus 2 r dot, and then times q dot. There we go. Okay. Alright, so we're doing good so far. Not too bad. Now, so what is Qi dot? Well, recall that the whole thing is moving, so it could be rotating maybe, okay? And so what I can do is I can write Qi dot, which is, another way to think of it, is the position, or it is the velocity of particle 3 from the perspective of the center of mass. Right? That's what Q3 dot is. So Qi dot is equal to, right, Qi in magnitude times omega. So Qi dot squared is this. Right? So I can make this a magnitude, which is Qi dot is equal to the distance between the axis of rotation and the particle itself, which is the length of qi, times the angular velocity of the whole object about that axis of rotation, which is omega. So I can write it like this, and so this becomes, I'm going to just write qi without the vector. So we get this. Okay? And so, when I put all this together, I get, this is equal to, so d by dt of Ri squared is equal to this. So r dot is the velocity of the center of mass, capital R dot. So this is v center mass squared. This guy is this, plus qi squared omega squared. And then this is equal to, well, we'll keep this for a moment. So this is plus 2r dot times qi dot. And you'll see in a moment that this is going to be the important thing. And this is going to cancel out just like we had before. So what happens when I sum them all up and add them all together? Well, I get k total is equal to, so 1/2, we'll do it term by term. So 1/2 the sum of mi times v center mass squared, plus 1/2 times sum of mi qi squared omega squared, plus the 1/2 cancels with the 2, the sum of qi dot times r. Remember that r dot is, it doesn't depend on which I you're talking about, so the sum is really over this guy. Okay, so there you go. So my claim is that this term is equal to 0. Because remember, this is equal to the time derivative, this term, is equal to the time derivative of, I can take that out and I get the sum over all the i's of qi. Not dot, just qi. Right. But qi is, go back to our definition, qi is Ri minus capital R. And so this is really d by dt of the sum of Ri, I'm sorry, this should be an mi in here, I'm sorry, my fault, mi qi mi times Ri minus the sum of mi times R, which is the exact same thing. This quantity here must be equal to 0 by the definition of what R is itself. Right? If you look, if you remember here, we said this is equal to 0. That's exactly this, also equal to 0. So this term cancels out. And we're left with only these two. And so let's do a brief analysis of this real quick. So that means that k total, that's a weird looking k, is equal to total 1/2. Look, the V center mass is independent of the particle I. It's just the sum. This is the total mass, 1/2. Total mass, V center mass squared. This is the moment of inertia about the center of mass, plus 1/2 I center mass omega squared. And then that's it. Right. So you see that the total kinetic energy factors into the translational kinetic energy of the center of mass, plus the rotational kinetic energy about the center of mass. The reason that we can't do this about any point is because this qi can't be the vector that points from just anywhere to the vector to the mass 3. It has to be the one that points from the center of mass to the to mass 3, because only then will we get this cancellation here. Right? If in general r was not, if this wasn't r, if it was some other vector, any other vector, then this minus this would not equal 0, which would mean we would have 3 terms. It would be like a cross term thing, and so we wouldn't be able to separate the translational motion from the rotational motion. The only way that works is if we use the location of the center of mass to calculate both the kinetic energy, the translational kinetic energy, and the rotational kinetic energy. Okay, so that's where that's important. And just to recap, for the first part, when we did this parallel axis theorem, once again, the fact that we only have 2 terms, which is to say that we have the moment of inertia about the center of mass plus m little a squared, is a direct consequence of the fact that this guy cancels. And so if we try and calculate this using any point other than the center of mass to be like our reference spot, then this will not cancel, and there'll be this plus ma squared plus some other cross terms that is no longer 0 now, and so we can't factor it like that. All right? So that's extremely algebra heavy, but what I really wanted to try and do was just illustrate to you guys where the center of mass comes into play, where the center of mass comes into play when you're talking about the parallel axis theorem as well as the rotational kinetic energy. So I'm not sure how effective this is going to be frankly honest with you guys, but maybe 1 or 2 of you can get some extra insight, which is well worth my time. So there you go.